All right. We'll go ahead and get started. How's everybody doing? Good Friday? Yeah. Who's flying out today? Awesome. Hope you enjoyed Chicago. If you're looking for Azure storage, performance, scale, security, you're in the right room. Congratulations. Hopefully this will be valuable use of 75 minutes here. What we're going to talk about, just a very brief storage overview. There was a storage overview talk on Tuesday. If you get to the end of this and you're like, that seemed like great content, I'm just not entirely sure what this Azure storage thing is, go back and watch that talk, then watch this one again. We're not going to spend a whole lot of time on that today. Then we're going to dive deep into the internals of storage, how it all works, some design principles, how you can use that architectural knowledge to your application's advantage, some more best practices. Then we're going to do some just 5-minute fixes. There's a lot of things that you can do in the code for your applications or using it from PowerShell, things like that, that will really make a big performance improvement in your applications. We'll actually walk through one thing that improves just a restructure of the code that makes things run about 5 times faster. We'll run through another one that makes it run about 99% faster. So definitely stick around for that. And then at the end, we're also going to talk about some security. We've been getting a lot of questions about how do I make sure I'm using Azure storage in a secure fashion. So we wanted to add that on as well. So that's all we'll cover today. Before we start, as I said, thank you very much for coming. It's Friday. Just on the behalf of everyone here, thank you very much for coming. Thanks for making it a great week. I've talked with, I'm sure, a lot of you at the Expo booth this week. Great conversations. Really appreciated talking with all of you. So thanks again. Azure Storage overview. Before we get into that, just 10 seconds about me. I'm Jeff Irwin, program manager on the Azure Storage team, have been for about 4 years. Before that, I was actually working on building one of the first applications that was ever built on top of Azure for about 2-3 years before that. So I've got about 6 years working with or on Azure Storage. So Azure Storage, as I said, just in brief, as a reminder, it's a durable cloud storage for your application. You can put 500 terabytes in one account, so high scale. If you need more storage, just create more accounts. No problem with that. 3 consistent copies in one location, plus optionally 3 more copies in a second location hundreds of miles away. And it's available from anywhere via HTTP, HTTPS. You can access it from anywhere. Large scale, millions of transactions every second. In fact, I didn't put the number in there, but right now we're handling an average of over 5 million transactions every second. Anybody with a calculator handy can figure out how many transactions we're going to do during this talk, but it's a lot. Trillions of objects stored as well. So we're really high scale. That's worldwide. We'll be able to handle quite a bit that you can throw at us. And flexible. We've got REST APIs for all the different data types. And then on top of that, just so you don't have to keep rewriting the same code over and over, we've got fully supported libraries, .NET, Windows Phone, Windows Runtime, Java, Android, C++. We just rolled out a preview of iOS and Xamarin. So we're getting more and more all the time. C++, Node, and Java all run just fine on Linux. So as you've heard all week, we're really happy to be supporting Linux in the cloud, and that's no exception here. And we're always working on more. So, storage types. First, we've got a couple of different options for what we call unstructured data. That'd be files, CSVs, contents, logs, just ordinary file system type data. First one and simplest one is just blobs, a block blob service. This is just blobs. To us, it's just bits. You organize it in a directory-like structure, and off you go. So simple there. Then we have the new files service we released at preview at last year's Tech Ed. This is very, very similar to the BlockBlob service, except it also has a SMB endpoint on it. So it supports the SMB protocol, which means that from within the same Azure region, you can actually address it just like a file share. So it really helps with migrating your applications to the cloud. If you've got some application running locally, it's talking to a file share, you can move the data and the application up to the cloud and don't have to change any code. You can keep talking to it just like a file share. Last week at Build, we actually announced technical support. Even though we're in preview, we don't normally do that, but we're confident enough in it now. We've added technical support for EA customers. So definitely check that out. We'll be GA soon. Next one, disks. So this one's been around for a while, but some new tricks around it. Disks is going to be used from your infrastructure as a service VMs. So all the Azure disks that you're using to support your OS drive, your data disks, those are all actually backed on Azure storage. They live in Azure storage. They're actually page blobs underneath. Page blob is just a special kind of blob that's optimized for being able to do random writes. So you can do random writes within the blob. Block blobs aren't so good at that. Block blobs can do random reads just fine, but if you've got random writes, you use page blobs. That's what disks use. Structured data, we've got tables. We'll actually talk quite a bit about that today just as a use for example. All the patterns that we talk about today are applicable to all of these data types, but tables is the one we'll use as kind of the primary example through a lot of the samples. Tables is a NoSQL store. What it's optimized for is really fast key value lookups. If you have highly relational database data sets, absolutely, SQL's still a great option. Still look to SQL for highly relational data. If you have a large volume of structured data, row-like data, or you just need fast key value lookups, you've always got an ID and just need to be able to look it up, tables can be great for that. It's also quite a bit cheaper than most SQL-type solutions. And then finally, we've got queues. Queues is a little different than the rest. It's mostly for messaging. The nice thing about it is because it's built on the same stack, it's got the same durability of all of the other data types. So you write a queue message, it's instantly 3 copies across the servers, so you know that message isn't going to get lost. As I said, these are all built on the same platform. So the same architecture, same hardware, these are all built on the same platform, which means they all have the same durability and availability characteristics as each other. So, yeah?
Just a quick question. You got logs listed on blob,
yes.
block blobs, but not on page blobs where you're going to be randomly writing to a log.
Yes.
Be better to put it on a page blob?
So the question was, just repeating for the audio, the question was, why is logs on blobs instead of on disks? I'm glad you asked. I actually have a sample for that a little bit later. So we'll go through that. Just as a note, we are going to try and leave, it's a great question, we are going to try and leave questions for the end. A lot of content to get through, so I want to make sure we have time for that. I'll stick around for however long you guys want to keep asking questions after. So, now to the internals, as I said, really brief overview. If you want more, check out breakout session 2458. That was a colleague of mine, Vamshi, did a great job on Tuesday, so check that out online. Also, of course, Azure.com. Check out the storage page. Lots of good resources there. All right, internals. Why internals first? Feels like a lot of talks. You're going to start at the high level, and then you're going to kind of dig your way deeper. This one, we're going kind of exactly the opposite. We're going to start as deep as we can go and work our way out. The reason for that is I've talked with a lot of developers, a lot of customers over the years, trying to work out a design pattern for their application. We'll talk, in the early days, I would talk for, half an hour, 2 hours, 3 hours, trying to help them understand why a particular approach was going to be better. It would make no progress. And then finally, I'd spend about 10 minutes, 15 minutes walking through the architecture of the system, how it works, and then they were telling me the right solution once they had that. So for this session, we're going to skip the 3 hours where I make no progress and hopefully get right into the architecture so you guys can make great design choices for your applications. There's one note there, common platform, again, you're going to hear me say that a lot. Common platform means even if you see a sample up here where I'm talking through tables or talking through blobs, any of the principles are going to be applicable to all of the different data types. You can apply it to disks, you can apply it to files, you can apply it to queues. All of them are going to apply across all the different data types. I'm just using different data types to kind of drive home the point. Storage architecture, 3 tiers. We've got a front end. Front end, stateless. It's a bunch of servers. They handle the request. They'll do, they'll handle auth. They'll make sure that the request actually makes any amount of sense at all, that it's not just garbage being thrown at our servers. It'll do the request metering, counting transactions, counting ingress, counting egress. That's all handled at the front end. Very lightweight and stateless. Then we've got the partition layer. That's what we're going to talk about a lot today. The partition layer is what actually really does the heavy lifting for the service. So it's the thing that actually handles the request, understands it, and decides where to go get the data or where to go put the data once it's handled that request. Having this partition layer is what enables us to have strong consistency even across a distributed platform. So you'll see how that works over the next few slides. And then finally, we've got the stream layer, also known as the data layer. This is where the data actually lives. So this is where we actually put 3 copies of all the data. This one, you'll actually see, knows very, very, very little about the data. It knows almost nothing about the data. It doesn't care whether it's blobs or tables or anything like that. To the data layer, it's all just data. So partitions. What are partitions? Can't say this first bullet point enough. It is the single most important concept when understanding how to design your data, how to design your application, how to work through things. Your performance will be dictated by how well you use partitions. Next 2 points kind of get at the crux of the issue. A single partition, and we'll define a partition on the next slide, next couple slides. Single partition is always served by at most one partition server. So you've got one server, and that single partition will always be served by one partition server. It can't be split across multiple partition servers. A single partition server will serve multiple partitions. So you'll have a server serving many partitions. That's okay. The scale of a partition is limited to what a single partition server can provide. So anything in the same partition is bound by what that single server can do. So this means data in a single partition can be updated atomically. You can do batches. You can do a lot of interesting things. You can get that strong consistency that we're talking about. But data in separate partitions can be load balanced. Azure Storage is an auto load balancing platform. You don't have to tell us what to load balance. We'll do it based on the real-time load that we're observing. We'll balance the different partitions across different partition servers to get great throughput. But again, if all the data is in one partition, we can't do that. We're bound by the desire to have all the data in one partition. There is no limit. We'll come back to this later. There is no limit on the number of partitions you can have. No problem to have millions, tens of millions of partitions. Not a problem. Don't be shy with the number of partitions. What is a partition? We're already talking about partitions, haven't really defined it. For blobs, a partition is simply the full blob path. Each blob is a partition. What that means is as you're doing operations on the blob, you're adding blocks, you're doing an upload that's adding blocks at a time. You're not uploading all in one request. You call put block list. All of that's going to have strong consistency across it. But each blob is its own partition, means we can always load balance any given set of blobs that we need to. Disks, a disk is a blob, and so a disk is a single partition. That'll become important when we talk about getting great scale out of Azure disks. Tables. Table entities are the obvious one. We actually have something named partition key, so that one's fairly straightforward. Each partition key you use is a single partition. Again, no problem with having millions or tens of millions of partition keys, even within a single table. That's totally fine. Queues, it's a single queue name, and files, each file share is a partition. So let's walk through some examples. Let's see how this actually looks in our architecture. We'll be basing this on tables, but again, you could apply it to any abstraction. So first sample request you see here, we've just got a random request here. It's for something in partition F, row 102. So that comes into FE2. That's completely random. Again, FE is load balanced. It's stateless. That request could come into FE2 this time, FE4 next time. It can really go wherever it wants. But right now, partition server 3 is what's serving partition F, which means that request, no matter which FE it went into, has to go to partition server 3. Partition server 3 is the one that is handling that request. It knows where to find the data, and so it can handle that. And then the data in this case happens to be on stream server 2, could be anywhere. Second request, same partition, different row. This request happened to go into a different FE. Again, it's load balanced, but it goes back to the same partition server. Partition server 3 is the one handling partition F. And then the data happens to be on stream server 4 this time. There we go. Request for a different partition. You can start to see what's happening here. Goes into a different FE, goes to the partition server serving partition T. This is partition server 4 this time. And its data happens to be over on stream server 2. That's where a piece of data that we've already seen was. That's, again, pure coincidence, happenstance. The stream server, the stream layer, doesn't really know anything about the data. It doesn't care. The partition server does. And then finally, we'll get more into this later. This is what we'd call a batch request, or a get entities request. This is a request for two different objects within a partition, where we've said, I want both rows 213 and 672 in partition W. That's going to get served by partition server 5. But then the data doesn't necessarily have to be on the same stream server, so it may go across multiple stream servers. This is going to be less efficient than the previous request we walked through, because we're getting more servers involved, having to go to multiple places to get the data. Azure Storage is going to be the most efficient when you're doing single object operations, single object requests. Anytime that you can keep your requests to one object, it's going to be really, really efficient, particularly with tables. Those single object, single row gets, single row inserts, really, really efficient. Table storage, actually all of storage is really efficient for that. As soon as you start going across multiple objects, it's going to get a little less efficient. When you start going across partitions, it's going to get really inefficient. We'll go through that more on the upcoming slides. So what does this mean for how you design your data? So let's start with just a simple table structure, just to remind everybody, or those of you who are coming from blobs or queues or disks. This is kind of how tables end up looking, and we'll be using this as examples going forward. This is just a very simple table. It's some sort of social network construct. We've got friends in here. We've got users. So we've got a partition key of a user ID. User ID happens to make an awesome partition key. Don't be afraid to use the user ID, an email address. If you want it, if you feel like it's not random enough, you can always hash it and use that. But there's no need to do, I've seen a lot of people do like prefix. They'll only take the first two characters and use that as a partition key. No need for that. Just use the user ID as a whole. As your partition key. That works great. So entities with the same PK, this user ID 1 always going to be served by the same server. The user ID 2 could be served by a different one. The row key, in this case account, uniquely identifies the entity within the partition. So within each partition, you have a row key to say which object we're talking about. In table storage, each entity contains some set of properties that's nothing but a set of key value pairs. But also in table storage, you don't have to have the same properties for each entity. There's no schema applied, so you can have different properties for different entities. That's totally fine. That's just a quick overview of table structure. So let's talk query scenarios. We're going to walk through point queries, partition scans, table scans. So different table here. This one we've got US cities. Apologize, it's a little West Coast centric. My West Coast geography better than other places' geography. That's the only reason for that. So in this case, we've chosen partition key of state, so the state of Washington, state of Oregon. Then we've used a row key of the city. And then we've got some properties there. Right now we've only got population, but obviously you could add a year founded and all kinds of square miles and things like that. So just a very simple table here. Let's talk through what this looks like. If I want to get data about Seattle, Washington, that's really easy. I say my table is US cities, my partition key is Washington, the row key is Seattle, and you can walk through, like we did before, exactly what that's going to look like. We have to go over to partition server 5 because it's serving partition W or partitions U through Z, which would include Washington, and then the row key of Seattle is just the object, happens to be over on stream server 2. Super efficient. One object from one partition, no problem here. An insert or an update of this object would be just as efficient. No worries about that. So you can do gets, inserts, anything like that. This one's a little less efficient. This one we've said, I want cities in Washington, but I don't want a specific city. I want all the cities that are bigger than 10,000 people. When I do that, then we're back into talking about partition scans like we had before. Still one partition server because we specified a partition key equals Washington. But in this case, we've got no row key. There's no specific object defined here. And so because of that, we're going to have to go across multiple stream servers. Involve stream server 2, stream server 3. This would be equivalent to, if the last one on the blob service was equivalent to like a get metadata for a blob, this would be more equivalent to just a whole get blob on a large blob that may be spread across multiple stream servers. So it's still okay. We're happy to do this. Still only one partition server involved, but it's going to be a little less efficient than that single object get. This is where it gets really bad. Now we have no partition key. So we've taken away the partition key. We've just said, get me all of the cities in the US that have more than 10,000 people. So this one's very simplified. I've only involved 3 partition servers. In reality, I probably should have involved all of them. But for now, I just threw 3 in there. But it's involving multiple partition servers because I have no partition key specified. It's involving multiple stream servers. That, again, probably should have involved all of them. And so you see this just many partition servers, many stream servers. In reality, what you're going to get is continuation tokens. You'll have to make a call. It'll give you one set of results and a continuation token. You'll call back with that, get the next page of results, call back, and keep calling and keep calling. These are not efficient at all, and you want to avoid these. If we're talking blob service, the equivalent to that is a list blobs. So list blobs, list queues, anything like that. Now you're starting to go across partitions, and it's not going to be very efficient. So you want to avoid those whenever possible. What happens when you scan? Why do you want to avoid them? Why not just say, oh, I'm fine with doing scans? First one, they're just inefficient. They take longer. So if you can avoid them, you'll improve the performance of your application. The second one is the scalability limits. So we say on table storage, for example, we say we can handle 20,000 entities per second per account. But that includes all entities scans. So if you're scanning 1,000 entities and only returning 1, that counts as 1,000 towards your scalability limit, not 1. So if you're doing a lot of these scans, you're going to be running into that scalability target pretty quickly. You'll start getting throttled, not going to be a good user experience, not going to be very efficient. So let's talk a little bit about how to avoid those. So in this example, we're going to turn a table scan into a partition scan. We said partition scans aren't as efficient as single object calls, but they're much more efficient than a table scan. So let's try and do that. So there's a word at the top of the slide here that probably made a few of you cringe. It made me cringe the first time I heard it. The word is pronounced denormalization. I know that's not a friendly word in a lot of rooms, but in this room it's a great, great word. The benefit is if you denormalize the data, you can query more efficiently. You can query based on the keys that you actually have rather than not knowing and having to do a scan. Unlike relational databases, table storage is very, very cheap. Even if you do RAGRS, that's read access geo-redundant storage, so you get 6 copies spread across 2 regions. You have a 4 nines read SLA. You can read on the secondary, everything like that, 12 cents a gigabyte per month. So very, very cheap. So duplicating data, probably okay. So let's look at how this can help us in the design of our application. So back to our US cities example. In this case, the PK partition key is the state name. Queries across states require table scans. So as we said before, if I want to get all the cities bigger than 100,000 people or 10,000 people, I have to do a table scan. No other way to do it. In this case, I've said, yeah, but table storage is cheap. So sometimes I'm doing queries based on the actual city and state name, in which case the data I had before is great. But sometimes I'm doing queries based on population. So in this case, what I've done is I've created a second set of entities where I've inserted each city again based on its population. So now if I know what population range I'm trying to get, then I can do a query that's just a partition scan. So in this one, afterwards, I say, get me all the cities that are between 10,000 and 100,000 people. Now this is a nice, much more efficient partition scan, not a table scan. So this is going to be much better than what we had before. So we've improved the performance through denormalization. We've avoided the table scan. You can do the same thing if you have data that feels like it's partition data. You can use the same tricks to turn partition scans into point queries. That's a little bit trickier and also less needed. Partition scans not nearly as expensive as table scans. But also, you also see this cost effectiveness and scalability of table storage allows for that duplication of data. So that's going to be okay. You can do exactly the same thing for blobs to avoid list operations if you're looking for it based on a different parameter. You may just want to create a copy of the blob with a different name based on what you'll actually be looking it up by. So next thing we're going to talk about is what we call query-first design. So this is going to be how to structure your data. This is really the crux of, okay, now let's try and apply this to build our data in a smart way to give ourselves great application performance. So in query-first design, before I get into this slide, query-first design, if you're coming from a SQL background, if you're coming from a SQL background, you'll actually, the way I've always thought about things in SQL is I design based on what the data is. I design based on the objects. I create this nice normalized form. Again, base it on what the data is. In Azure Storage, you want to base it on a different factor. You want to base it on what questions am I going to ask, right? What are my queries? And then design the data to be able to answer those queries quickly. Again, if I need to store the data twice, that's okay. The storage is cheap, but you really want to design for your queries, not design for this nice object model. So in this case, we're going to talk through an example. This is actually a real example. I can't say what customer it was, but this was something that we really encountered a couple of years back. Customer orders with a retention policy. So imagine I'm running some sort of e-commerce sort of thing. I've got customer orders, and I'm going to be doing a couple different things with it. One, I'm going to get status of a recent order ID, right? So has it shipped yet, or can I cancel it, or something. I want the details for a particular order ID. I'm going to know the customer ID. I'm going to know the order ID. That's going to be a really frequent one. Sometimes a customer is going to ask me, get me all of my orders. That's pretty infrequent, so we don't really need to optimize for that. It happens, but not very common. And then there's an additional kind of complicating requirement here that we don't normally see. For privacy reasons, security reasons, we have to delete any orders that are older than 6 months. So anything older than 6 months has to go. So we've got to be able to clean this up fairly frequently. So let's take a first try at this. Perfectly normal table here. A good first attempt. This is absolutely what I would try on the first try, is just give a user ID. As we said, that's a great partition key. Row key is an order ID, and then throw the properties in. So this one is really good for finding a particular order. It's really good for finding all of a customer's order. What it's not good at is enforcing that retention policy. To find all the orders to delete, I have to scan all the orders in the table. It's a table scan to do that. And presumably, that's a query I'm going to have to do every single day to make sure that everything's old. If we're at scale, we're a very successful e-commerce company, that's going to get really expensive and slow us down. So let's try this a different way. So this was the solution that we used in that particular case. Instead, we said, let's create one table for every month. So every month, we'll create a new table. So you see January and March up there. Just assume February and April and May are all up there too. What this ends up doing is, now to enforce my retention policy, when one table gets 6 months old, I call one call, delete table, right? And I call delete table. That's really efficient. And I already know it's 6 months old by definition. I create one new table every month. I delete one table every month. Instead of doing a table scan, I do 2 operations. Much, much more efficient. Now, one thing here has gotten less efficient. That's finding all the orders for one customer. That's not as efficient as it was before. It requires a partition scan across each of the tables that I've got. That partition scan across each of the tables is still much better than doing a table scan. And as we've already said, much less frequently used than the retention policy. So this is a good trade-off. And if you really needed get all the orders by the customer, we would do what we did before. We'd go ahead and just duplicate the data, keep another table that allows us to get all the data. So a lot of options here. Hot partitions, let's talk about these for a minute. What is a hot partition? Single partition taking much more load than any other partition in your data. This could be a single blob, a single queue, a single partition key in your table, single file share. These you want to avoid. Why? As we talked about before, you necessarily limit the scale of that partition because we can't load balance it across servers. So you're going to get stuck by what one partition server can do and the partition scalability limit. So why do we want to avoid them? Can't scale. So let's talk logging. Said we'd come back to it. So logging, we're going to talk about an example of hot partitions here. The example we're using, high-scale logging from servers. Got a bunch of servers. They're all writing logs out to storage. Great place to put logs. Cheap. You can keep a lot of logs. So let's talk about this. First try on logging. Let's use tables. It feels like structured data. Let's use tables. So on this one, you see an interesting thing happen. You see we're using a partition key of a date. Feels kind of natural. Row key of a time, again, feels kind of okay. Makes my querying pretty easy. Not a problem. The problem with this is, in my experience with logging anyway, and I think in a lot of applications, writing new log events is far more common operation than getting the logs. What this is going to end up doing is it means all of the inserts are always going to the same partition, right? They're all going to the partition representing today's date. And so that means that my scale of my logging system is now always going to be bound by what one partition server can do. There's no way around it with this design. Maybe fine when you're starting out, but again, we want really successful applications, high scale, and this design won't do it. So note that in this case, this is still true even though that partition key changes every day, right? So the partition key is new every single day, but there's still only one, right? So we have just no ability to load balance, no ability to help you out. So let's try this a different way. Still with tables, now we're splitting it out and giving each server its own partition key. This is going to be better. It's going to perform better. It gets away from that hot partition, solves that problem. Tables is really good for key value lookups, like we said before. It's not, you can do partition scans. It's not going to be that efficient at it. It's not the best model for this. In logging, how many times have you ever done a log lookup where you've looked for a single log event, right? Where you said, get me that log event from that time. In my experience, that's not very common. Usually what I want is give me all the logs around this particular time so that I can kind of see what was happening. So this is not going to be all that good at that. So let's keep going. In this example, we use blobs. We don't have to answer the question from earlier, we don't have to use page blobs because all of the writes are always at the end of the blob. If I was writing into the middle of the blob, then I would want to think about page blobs. So if you've got time series data, I've seen this used before, you've got time series data, you may need to go back right in the middle, things like that. Then you can definitely look at using page blobs. Absolutely. Good solution for that. But if you're always writing to the end, blobs are going to work pretty well for that. So in this case, now each blob represents a 5-minute chunk. They're being cached on the server and then written out as a blob every 5 minutes. This is going to be much better for our retrievals, right? We're getting one whole blob. That's very efficient. Nothing to worry about there. Soon, we're going to have a new one. You can go out and read our blog about append blobs. So append blobs was actually designed for exactly this scenario, which is now it's just like a block blob, except it supports one additional API, which is append block, which says, take the existing blob, and now I want to, in one transaction, strongly consistent, add more data onto the end. It was actually designed exactly for logging, and now you can say, okay, each server gets one blob, and it's just going to keep appending until that blob gets to be 200 gigabytes, and then it's going to need one more, a new blob after that. You could, if you wanted to, in this one, you could actually use one blob for everything. You could have all your servers writing to one blob, but remember, though, one blob is a partition, right? So that one blob can handle up to 500 requests per second, up to 60 megabytes per second. If you're going to be coming up to that limit, think about doing this instead. Give each server its own blob, and then make requests across those blobs if you need to. So a few different options here, but one of the things that we see here is that sometimes the right way to use storage is, even if data feels like it's structured data, think about blobs instead. If you're going to be doing batch writes and range reads, blobs is going to be much better at that than tables. Data design summary, all the things we've talked about so far. Choose great partition keys. Get the right blob path, the right table keys, the right queue name. We didn't talk a lot about queues, but you can do the same thing with queues. If you've got one queue that you think is going to be high throughput, start building out multiple queues, right? Start using multiple queues for those requests. Do a little bit of sharding across those. Partitions are the limiting scalability factor. And again, I'll say it one more time. Table can have millions and millions of partition keys. A user ID, a GUID, all great partition keys. Those are awesome, gives us full flexibility and load balancing however we need to. Denormalization is good. Use the right abstraction. Think about blobs, think about tables, think about files. Do what's right for your application and how you're actually going to use the data. Think about your queries and then design the data. So now let's talk about, we're going to start deep and then kind of work our way back out. Now we're going to take one big step on our way back out, and we're going to talk about application design. So look at it from kind of the outside of the system. So one thing that we've seen can make a world of difference in a lot of things is queues. You can use them for messaging. That's great. You can have a front end go to a back end and things like that. But what we see here is the crux of the issue is anytime you've got processing that needs to happen eventually, it doesn't need to happen synchronously in line with whatever the user experience was. Queues are great for that. They can make your application much more responsive because you can send that work item to be done off to a queue and let some back-end processor take care of it. You can use this for creating secondary indexes. You can use it for change notifications. You can use it for, I've got some photo I'm going to upload, and then I want to create thumbnails. I want to virus scan it. I want to do any number of things with the data that the user has given me, using queues and then letting some back-end worker process that data completely, get the eventual work done is a really great way to do that. High-scale fashion, right? Because now we actually support auto-scaling. If you're using PaaS, we actually support auto-scaling based on queue depth. So you can actually do auto-scale, and then that's all even automated. As your queue gets deeper, it'll spin up more workers and be able to chew through that queue faster and get you back to zero. So queues work really great for work that's long running. Distributing content. So this one, if you went to, there was a breakout session on hyperscale computing earlier this week. This is something that those guys are running into a lot. So if you're in that camp, this will be useful. If you've got one blob that needs to make it to many VMs, you're going to run into a problem again, right? You're going to run into that 60 megabytes per second. If you've got to get out to 1,000 VMs, that's just not going to cut it. Best thing to do, make multiple copies of the blob. So one piece here is don't just call copy blob within the same account. Those of you, I've had a couple of you walk up at the expo and you said, sometimes copy blob feels really, really fast, almost like it's creating a new pointer to the same data. There's a reason why it feels like it's almost like creating a pointer to the same data, because it is. So doing that will not help you get past that 60 megabyte per second limit. So if you need this, then create multiple copies of the blob individually. Upload it twice, put them across storage accounts, things like that. If you've got many blobs to go to many VMs, this is actually much easier to solve. Randomize the order that you get. Don't just get them in lexical order, because then you'll have that hot partition problem that we were talking about earlier. They'll all start from the first blob, then they'll move to the second, then they'll move to the third, and they're all going to be fighting over the same resource, the same partition server. Have your VMs download the blobs in different order, and that way you're spreading your load across the whole blob set. You can use that in the first scenario we talked about. If your blob is very large, cut it up into pieces, right? So if you've got a gigabyte blob, 10 gigabyte blob, cut it up into 10 megabyte, 50 megabyte chunks, whatever makes sense for your application, and then have your workers download each of those blobs individually and reassemble it in the worker. That'll get you much better throughput. Same blob, many public users. This one, use a CDN. This one's pretty straightforward. If you're distributing blob out to end users, don't try and use Azure storage to distribute that to end users. We do support public blobs, mostly so that you can put a CDN in front of that. So if you've got content, videos, images, things like that, use a CDN for that. That'll be great for your users. They'll get lower latency once the cache gets warmed up, and you won't be running into these scalability limits of the storage platform. Disks. This one, I'm going to refer you to the talk that was last night at the end of the next slide, but just really quickly on disks. 500 IOPS a disk, 20,000 IOPS per account. Don't put more than 40 disks in one account. That's not going to work very well. You'll run into the account scalability limit. To avoid the per disk scalability target, use storage spaces to stripe across disks to get more IOPS. That works really, really well. And then avoid that account scalability target. Use multiple storage counts if you need to. No problem. Premium disks, now GA. We GA'd it a couple weeks ago. There was you can see the code on the bottom there, breakout 4450. My colleagues Ong and Sirius did a great job last night, deep diving into premium storage, much higher IOPS than standard storage, lower latency, more consistent latency. A lot of customers have been asking for this for a long time, but you can see, a P30 disk gets you 5,000 IOPS per disk as opposed to the 500 you can get in standard storage. Also goes up to 200 megabytes per second instead of 60. Lower latency, more consistent latency. And again, you can do the same things. You can stripe it. They did an example last night. Vasu, what was the number that they ran it up to? 100,000 IOPS, 100,000 IOPS when striping across a number of premium disks. So check that out. If you're doing database workloads, or other just high I/O workloads, definitely think about using premium storage for that. So now we've gotten through the big meat of it, big architecture, internals. Let's talk about some really quick things. A lot of these are just really quick ways to improve the performance of your application. You can go back and do these all on your plane flight home, and you'll be much happier. So a few of them that apply to all services generally. Use read from secondary and don't overuse create if not exist. Let's look at what that looks like. People think about read from secondary as an availability trick. It's also a performance trick. When we load balance, many of you who are familiar with Azure Storage will know when a load balance event happens, you may see a few seconds where you'll get server busy responses, followed by much better throughput. So you may see that. But if you do this, you have a location mode for a request, primary then secondary. What you're telling the storage client, and this is our .NET storage client, but it exists in Java as well. I think the other languages too. What you're telling it to do is try the primary. If you get back a retryable response, a server busy or something like that, immediately retry it on the secondary. And what that'll do is, instead of having a few seconds where you're doing an exponential backoff, things like that, it'll just immediately go get the data on the secondary. Do be mindful, secondary is eventually consistent, which means data that's been written may not fully be reflected on the secondary yet. So if you've got data where it needs to be strongly consistent, this probably isn't such a good plan for you. But if you've got data where you're okay with whatever was a few minutes old, then this can be a really good way to provide a more responsive experience to your user. This one, I have made this mistake. I don't know anybody who hasn't, but do a scrub of your code for this. It's amazing how often it comes up. You only need to create a table once. You only need to create a blob container once, a queue once. Create if not exists always makes a server call, right? So there's no way around it. Every time you call create if not exists on a blob container, on a table, on a queue, it's going to make a server call. So I've seen a lot of code where it's, right before I'm uploading a blob, calling create if not exists on the container every single time. That's just going to slow you down. So do a code scrub for that. Update message. We talked about queues a little bit ago. This is a great way if your work is very long running. So if you've got some process, say it's a video transcoding, right? I've got a video, it was uploaded, now I need to make it available for other bit rates or other devices, and this is an hour-long video. It's going to take 15 minutes, an hour, 2 hours, or whatever this ends up being to finish the work of creating the new transcodings. You can use queues and then use what we call update message. Queues works on a two-phase delete model. A worker will retrieve the message. That makes the message invisible for some time. And then when it's done, it'll call back and delete. If that timeout expires, the queue message will become visible again because we're assuming that the worker has failed. It's died. It's not there anymore. And so somebody else needs to pick up the work and keep going through it. That's great. It means the message is durable. It means it's going to get processed. But it also means if you have something that's going to take you an hour, you used to have to go ahead and put an invisibility time on it of 2 hours. Make absolutely sure that there's enough time there to finish everything. So now if I have my worker pick it up, start processing it, and for some reason the server dies 2 minutes in. Now it's going to be 2 hours before another worker picks it up, plus 2 hours to process it. Let's really hope that server doesn't fail, right? And so now you're at 4 hours before completion. It's just going to make it a long time. So we don't want that. The other way it could happen is you get nearly done, right? You're an hour and 58 minutes in, you're almost done, and then it fails. And now somebody else still has to pick it up and reprocess the whole thing. Update message solves both of those. So update message allows you to update both the invisibility timeout and the contents of the message. So you could, within that hour, 2 hours, periodically, first only take an invisibility timeout of a minute. And then every 15 seconds, 30 seconds, call back and extend that invisibility timeout. Say, I'm still working, still working, still working, still working. And update the contents to say how far you got. Right? Say I got done with step 1, I got done with step 2, I got done with step 3, 4, 5, 6. Now, if that server dies, somebody else picks up that message very quickly, because it times out quite fast because we were updating the invisibility timeout. And it sees, oh, it's already done with step 5. I'll start with step 6. Don't need to start over from the beginning. So this way you can get much more consistent back-end processing. You don't have to worry about, well, what if a server dies? Is that going to make things go twice as long, 3 times as long? So you get much more consistent. So, copy blob, parallel block upload in blobs. So this is going to be about moving data around. Copy blob. People ask, okay, what's the most efficient way to copy data? So we have a method called start copy from blob. It's a asynchronous copy blob. It allows the server to make that copy for you. That's going to be great for your application scale because it means you don't have to download all the content and upload it again. We do that for you. You point us to where you want the blob from, we'll do the copy. That works really, really well. What it doesn't do is it is a queue-based system on our side, which means if there's a lot of people doing copy blob, it may be some time until we get to yours. So if you need that copy to succeed quickly, this probably isn't going to work so well. You may want to go ahead and download the data and upload it yourself from a VM in Azure so that you can get very consistent copy times if that's what you're after. But if you don't really care, you're okay with a little bit of a wait, use the server-side one. One model that I really like is try the server-side copy blob, wait a minute or 2, 5 minutes, whatever you find acceptable, pull, see if it's started. If it hasn't started, cancel it, do it yourself. That can actually work really well. Gets you kind of the best of both worlds. If we pick it up quickly, it'll happen quickly, and you don't have to do the copy. If we don't, you can still get the consistent time to completion that you need. Parallel block upload. This is super easy to do, and it's going to make things a lot faster. If you're doing a single blob upload, it takes just a couple lines of code there to say, upload the blocks in parallel, right? Increase the connection limit, increase the thread count, and actually the client library will handle everything from there. In this particular version, it'll do 8 threads at a time. That seems to be a pretty good number to use. This can make things much faster using multiple connections to speed things up. Remember what we were talking about partitions earlier, though. If you're doing a single blob, okay, this is good. If you're doing multiple blobs, leverage the fact that you're going across partitions or that you've got multiple partitions involved, and upload the blobs themselves in parallel, not the blocks for a single blob. And that'll allow us to load balance those partitions, upload the many blobs in parallel. Tables. Multiple point queries. That's a big block of code. The short version of what that code does is it's just a get for 2 different entities within one partition. So this is just a query that gets 2 specific entities, entities 00012 and 88763 from within one partition. So pretty straightforward. This is one request for that. This will do a partition scan, as we talked about earlier. This will scan all the partitions to find those 2 entities, or scan that partition to find those 2 entities. Not going to be very efficient. So instead, kind of counterintuitively here, just make 2 what we called point queries. Make 2 queries, each of which gets 1 single entity. That's going to be much more efficient. I haven't even parallelized these, and in one test from just from my dev box sitting in Redmond, performed consistently 5 times faster than the previous example. So if you've got need to do basically multiple point queries, think about actually doing multiple point queries. Don't try and put them in one big OR statement in one partition scan. All right, I told you we were going to make something 99% faster, so here we go. Inserting 1,000 entities. I've got a lot of data. Maybe I'm moving it from SQL or a CSV or who knows what, and I want to move it into table storage. So this is our first try. We're just going to do, I'm just inserting entities here with one partition key of standard and a row key of just a counter. So just as an example here. So this is our first try. It's just going to go through each number 0 to 1,000 and insert one entity. On my machine, dev box, this took 109 seconds, minute and 49 seconds. Okay, that's not great. We'd like to go faster. So first thing we're going to do here is we're going to turn something called Naegele's algorithm off. If you're not familiar with Naegele's algorithm is something that is basically says, I'm about to send a packet, the packet's not full, I should wait before I send it and see if there's anything else to join it. It happens at the network layer. It's really good for some things. It's really, really, really awful for tables, queues, small blobs, where your entities are frequently below that packet size because it just introduces a delay for no reason. You already know there's no more data coming for that packet. You'd much prefer the network layer to just send it immediately. So fortunately, turning it off is just 2 lines of code. If you want to turn it off globally, it's actually only 1 line of code. It's just service point manager dot use Naegele algorithm equals false. Have to call it before you make any calls. As soon as you make a call, it gets cached. Make sure that you make this before. Again, you can do this across languages. You can do it Java, C++, anything. Make sure that you've got Naegele turned off. Let's see what the impact is. Drop from 109 seconds to 42 seconds. Doing much better here. So think we can still go faster. I owe you 99%. Parallelism. So of course, we can do some parallelism. I'm just using here simply a .NET for each. Note that first blue line there, default connection limit equals 100. I've still got Naegele off. This is the 1-line version, turns it off globally. So in this one, using multiple threads, setting a max degree of parallelism just to be safe, make sure .NET doesn't go crazy, and use all my threads, all my resources. But in this case, nothing fancy here. Of course, you could write your own threading. I've just used a parallel for each just for the fun of it. And this one gets us down to 4 seconds. So doing much better here. And again, only a few lines of code here. Not much. You could, again, make this on the plane flight home. Now let's do batch transactions. Again, if I've got many entities that I'm inserting all at once doing one big upload, or if I've got a bunch of data coming in right now, I can batch it up, put it all in one transaction. Let's do that. So in this case, I'm just doing batches of 100 operations. Batches can be up to 100 operations, also a 4 megabyte limit, so be mindful of that. But in this case, we do batches, and we get down to 1.7 seconds. So now we're close to that 99%, but not quite, because of course we can do parallel batches, because why not? In this case, we do the batching, create some batches, we do a parallel for each, we're still executing batch, and in this one, finally, we get down to half a second from 109 seconds to begin with. Also, just look at the graph. All the previous ones had this nice linear rate. This one's actually really cool because we end up with this up to the degree of parallelism. You see a pretty long delay before the first one completes, and then all of them complete all at once, right? So you're going to get some really good performance when you do this. So definitely keep those things in mind. You can use all of them, none of them. Definitely if you're using tables, if you're using queues, even small blobs, please, 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 for your own sake, turn Naegele off. I'm sure it's useful for some applications. It's not useful for storage, and unfortunately, .NET at least turns it on by default. So just make sure it's off. You'll get a lot of performance gain just from that. Cool. That's performance and scalability. Now let's kind of shift gears here. We're going to talk about security. We're all done with partition scans, all done with table scans. So let's talk some security. So we'll cover some auth methods, shared key, SaaS, and public. And we'll also cover some new encryption options. A lot of you at the expo have been talking about encryption this week, so we'll get into that. So auth methods, we have 3. First ones are the oldest ones. They're very simple. We have shared key auth. Every storage account gets 2 shared keys. You use that shared key to sign requests, send the request with the signature. We validate the signature on the server and decide whether or not to allow the request. The shared key gives you full admin access. And the shared key gives anybody that you give the shared key to full admin access. So make sure that you guard the shared key as well as you possibly can, because as soon as somebody has it, they can do everything. But shared key is kind of the default. It's what most people use for now. We'll talk about in a minute some options that are coming. Then we've got public. As we said, if you want to put your data in front of, behind a CDN, you can change blobs, only blobs, not tables or queues or anything, but you can put blobs ACLed publicly, and then gets will work. Read access will work for those blobs. There's no public write access or delete access, read only, so that you can put a CDN in front of it. The very common use case for this would be images, JavaScript, CSS, resources for websites work great here. Shared access signatures. Shared access signatures allow you to give very specific permissions, delegate those permissions out based on what the user actually needs to do. They can be time-bound, they can be permission-bound, and it avoids having to give that shared key out to people that you don't trust with the shared key. So examples of that, you have a download manager, you want to give somebody read access to a specific blob for a few hours. A SaaS can do that. You've got a photo site, you want to allow a user to write a blob without you having to proxy it all through your web server. That's another good example for using SaaS. You can time-bound that to 30 minutes so they don't keep writing over and over. Big compute, you could give read-write list permissions to a container for a single day, anything like that. What's it look like? They're actually pretty simple. They're just URLs. So the first part there in blue is just the object to be requested. So this is for a particular blob. The second part there in orange is the permissions being granted. So you can see, if you can kind of parse that a little bit, there's a version there. That 2012-02-12 is just what storage version we're using. There's a start time, there's an end time, and then there's some read-write permissions on there at the end. So this specifies what the user is allowed to do with this token, and then the rest of it is just a signature. So that was somebody used their shared key to sign that permission string, that orange string, got the, is it yellow? Looks yellow. The yellow signature, and just throw that signature onto the end and then send the whole thing to whoever's supposed to be doing this access. Then they can send this to the server. The server will allow it if the signature matches what the server gets when it tries to sign that same string with the shared key. So this gives you the ability to delegate access, time down, works really well. So how does it work? There's the whole text description. I won't bore you with that. The last sub-bullet under the first main bullet has just the method you call. Really easy to create in all the libraries. Get shared access signature with the permissions handed in as a parameter. Really easy. Some notes. Shared access signatures are not stored. They are computed. What this means is you can have as many as you want. You can create an infinite number of SAS tokens. People frequently ask, how many SAS tokens can I have? The answer is as many as you want. They are computed. They're not stored. The owner of a shared key can create infinite number. There is such a thing as a stored access policy. I won't go to it here, but check if you just use your favorite search engine, Azure Storage Shared Access Signature. There's a best practices doc that'll come up pretty much right on the top. It'll talk about stored access policies. Basically allows you to give at least a hook to be able to revoke shared access signatures that you've created. So think about using those. 10 best practices real quick with SAS. Always, 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 always use HTTPS. A SaaS token will grant the permissions both to whoever you wanted it to and to whoever gets the signature. If they're transmitting that SaaS over HTTP, somebody gets it, that's not going to be great. So, and we'll talk about an option on the next slide for how to make sure that's happening. But always use HTTPS. Reference stored access policies where it makes sense. Make sure that you can revoke. You can always revoke all shared access signatures by rotating your shared key. So we allow you to regenerate your shared keys. That will cause all shared access signatures to break if you want. Better, just use a near-term expiration, right? Don't make them valid for longer than they need to be. We used to enforce a 1 hour on them, so the end time could never be more than an hour after the start time. People found that too limiting, but use the new power responsibly. Don't create infinitely lived SaaS tokens because you're just begging for somebody to get it and start using it maliciously. Always make your clients assume that at some point the shared access signature will break because the shared key got rotated, it expired, the stored access policy got deleted, who knows what happened, but have the client know how to call back and get a new one. So just make sure that you're not assuming, okay, I'm giving this one shared access signature out once, and they'll call back when it expires. Make sure they know how to call back if that shared access signature stops working. Don't use start time equals now. Clocks tend to drift. If our clock is different than your clock, then start time equals now may be in the future. And so somebody will turn around, start using that immediately, and our servers haven't caught up to when you created that yet, and the SaaS will fail. Flip side of that one, also on the end time, don't create SaaSes that are too short-lived, like 5 minutes or 2 minutes or something like that, because again, you're in that clock skew window. We generally advise always give at least 15 minutes for end time. For start time, unless you're really trying to do future SaaSes, you're trying to say, sometime next week I want you to be able to do this, which is a pretty rare scenario, just leave out the start time. If you leave out the start time, it's effective immediately and until the end time. There's no problem with doing that. Don't give access to more objects than you need. So this is one of the beauties of SaaS, is you can give it for a specific object, a specific container. Absolutely use that. Don't create one SaaS. This will become more important on the next slide when you can see what we're releasing later this year. Validate any data written with SaaS. You're turning this into a direct user write. Make sure that when you're reading it, you're doing some validation, making sure that there's nothing bad in there. Understand the build usage, right? Any usage that's done with that SaaS will get billed to you. So even if you gave that SaaS out to somebody and they start doing something, the bill for that is going to come to you. If they're reading the same blob down over and over 10 times from outside the data center, you're going to pay for all that egress. So use that near-term expiry to make sure that that can't happen. And also just don't give out the SaaS if you don't trust the user, right? There's no problem. You can still proxy the data through a web server. That's okay. If you can't trust the user, don't give them a SaaS token because you don't know what they'll do with it. And then last thing, you can always use storage analytics. We have storage logs. Use that to monitor for threats. You can pull down the logs, be processing them, use a backend worker role, anything like that. Process through the logs and make sure you don't see anything odd in there that makes you think that these aren't being used responsibly. One thing that you can check for really easily is check for anything that used SaaS authentication that was being called over HTTP, right? So that's something that should never happen. Really easy to watch your logs for. SaaS improvements. These are all things that you and other customers have asked for. First one is an account SaaS. This goes directly against a bullet on the previous page, but sometimes makes sense. Account SaaS is give one SaaS token that's valid for the entire account. Most common scenario for this one that I think people are really going to love, you can now give somebody read access to the entire account. So as soon as we have this out, you'll be able to create one SaaS token, give somebody read access, maybe an operations person or somebody doing analytics. They'll be able to read everything. They won't be able to write or delete anything at all. So with that, there's very few reasons to use shared key anymore once you have this. And we would actually really suggest use SaaS everywhere you can. There's a few cases that I can think of where shared key kind of still makes sense, but even those, really think about using account SaaS. Second one, protocol SaaS, to help you prevent HTTP-based use of SaaS. You'll actually be able to tell the SaaS token, this SaaS token can't be used over HTTP. Obviously, somebody can still send it over HTTP. What it means is the server will reject it, which means any client applications that have been built incorrectly will immediately start failing once you start issuing SaaS tokens with this. But they should fail. They're very insecure. And then the last one, this is something people have asked for quite a bit, is a IP-restricted SaaS. So again, to prevent the risk where the SaaS token gets leaked, you can put an IP address or an IP range on the SaaS token and say, this SaaS token only valid from that IP. That way, when the server gets the request, if it came from some other IP, it'll just reject it, even if the signature was valid. So this gives you a lot of new ways to use SaaS, a lot of ways to make sure that your SaaSes are being used responsibly. We really recommend using those. Client-side encryption, last topic for the day. So with client-side encryption, we've got a preview. We released this last week, so good stuff. You can go home, try it today. Let us know what you think. Here's a brief introduction into it. Our goal is implement best practice encryption methods. So instead of everybody, this doesn't do, just preface on it, doesn't do anything you can't already do yourself. It's all client-side. There's no reason you can't do this yourself. But what we've done is we worked with all the Microsoft internal security folks, gotten a lot of reviews, tried to make sure that we're doing it right so that people don't have to keep implementing the same thing over and over. Encryption can be a little tricky. We wanted to make sure we're doing it securely in a method that'll work well for a lot of customers. So we've implemented best practice encryption methods. We've integrated with Azure Key Vault, key management system, so that should help you manage your keys. It's fully flexible. We can work with any key management system. You have to write a little bit of code to help talk to your key management system, but the encryption methods all will work with any key. So that you'll be able to use on-prem, hybrid cloud, anything like that works well. Big thing for client-side encryption, you control the keys, right? So anytime you start talking about encryption, the big question is who gets the keys, right? And if we were doing server-side encryption thing, well, it'd be your data, we'd encrypt it, but it'd be with our key, and so we have both the keys and the data. Maybe not that interesting. In this one, if you have data on-prem, you're uploading it to the cloud, but you want to encrypt it first, you upload the encrypted data, we never see the keys. In fact, the way that we've designed the client library never actually sees the keys. We call out to your code to have it use the keys. So we never see the keys. So how's it work? Envelope encryption. I'll let you read more about this on the storage blog. Basically, it means for performance, we're generating a symmetric key, encrypt your data with the symmetric key, then we call out to your code to encrypt that symmetric key, and we store the encrypted symmetric key with the data that was encrypted. Much more performant, but still highly secure. The encrypted, this is really important, the encrypted asymmetric key is always stored as metadata or as extra table properties. Means you don't have to have a second store for all this stuff. So it's all stored in line with the data as you store it. What's supported today? Blobs. We support full blob upload, range or full blob download. Tables, you can do it at the property level. You can tell us which properties to encrypt. Queues, we can encrypt the whole message. So a lot of options there. Here's just a sample. I won't walk you through it, but this is a sample just to show you how much code it is. This sample both uploads a blob and downloads a blob. It encrypts it and then decrypts it on the download. Very, very simple code. I think there's, 6 lines there. So, what's next? Your feedback, please. Please, please, please. We want to do this right. We want to make sure that this is useful as possible. Once we've got the .NET one done, we'll start looking at other languages, and we want to make sure that we've got the right solutions. So check the storage blog to get started, see more samples, see about the Key Vault integration. And then let us know on feedback.azure.com what else you want to see. What do you want to see supported? What do you want to work differently? Please give us your feedback. We've been doing internal previews in the last month, and we actually made some pretty significant changes to the tables encryption based on some feedback we got 3 weeks ago. So we're trying to iterate on this, make this work well, so please try it out. Let us know what you think. We want to get this right. Well, GA when it's right. That's the timing for GA. It's there. We do still need to stress test it, but that'll happen. The big thing is it'll GA when you're telling us that we've got it right. We don't want to GA before that and be stuck with the wrong schema and then find out, this isn't as secure or as performant as we want it to be. It doesn't do what we need it to. So try it out. Don't use it in production. Assume the schema will change prior to GA. If I couldn't say that, then I couldn't actually say I want your feedback. So that should come as a comfort to anybody who wants to tell us that we got it wrong. But assume that the schema will probably change at least in some way prior to it. So please don't start using this in production. Also, be really careful with encrypted data that you've uploaded. If you upload the data and then you were to say, change a block of the data, then that's not going to be very readable. So be really careful about making sure that if you're using the encryption library, you're using it for everything, not using it for some calls and not others. That's all I've got. Thank you very, 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 very much. Hopefully you had a great week. Some extra resources here. The first two links are really good. This talk is actually based on the first two links. It's kind of the in-person version of those two docs. Performance and scalability checklist has everything we just talked about and probably, I would guess, twice as much that we didn't talk about today. It's about 50 different best practices. You can use it like a checklist, print it out, 15 pages, go through and check off the list, make sure you're doing it. Table design guide is all kinds of table design patterns to make your table usage great. Azure Storage blog, always good stuff there. Some more sessions, the Azure Storage overview. If all this went over your head and you're still wondering what's Azure Storage, check that out and then come back and watch this one again. And then premium storage and developing hyperscale applications, also good talks to check out. So thanks, hope you had a great week. I'll be up here to answer some questions.